There was a question on images with an image not appearing. So I was going to talk about that. Uh, if you go into your File Explorer, you want to make sure your extensions are showing. That's an important piece. Um, how you do that is you got the view here, and then where it says File Name Extensions, you want that checked. Now, depending upon your version of Windows, you may have different ways of bringing this up. Like you can do an Alt key, and some of them will bring up this menu if you don't see it. Not so much PNG, but JPEG oftentimes has two possibilities. You'll see them stored off this way. Oh yeah, yeah. And then there's some that you'll find out there on the internet that you save that are JPEG. Um, so that's why you have to be able to see your extensions to make sure you're accessing the right file. Now the second thing is the image has to be in the same folder as the HTML. If it's not, then it won't find it. Like if I put this in a subfolder, I can access it via HTML, but I have to put that the subfolder on there and then my image name. I don't remember which one was my image, but let me go to it. Not able to get in. Yeah. Yours is still okay. Thought I had an image on here, but it's not. Oh, there it is. Now, this should be the format of it. You should have your less than a course, IMG, and then source equals. And this name here has to exactly match this name over here. If I don't have PNG, it won't work. Width and height aren't necessary unless you want to resize it. And then you have to end it with the slash greater than. Does all those match? Oh, you had everything else? Now, the extension should only be necessary if it doesn't match. So, like if you had pink here and not the .png, then I wouldn't. But if that one of those doesn't fix it, I can take a look at it and see what's wrong with it. It shouldn't take just a minute to glance at later. Um, mhm. If I already have it created, what I did is I right clicked on it and I choose Open With. And you probably don't have Notepad here, but if you choose another app, you can do the drop down, the scroll down, and go to the more apps, do that drop down there, And you should see Notepad somewhere there.
Okay, thank you.
Mhm. Yeah, because if you just double click on it, it brings it up in the browser.
Yeah, I was like, oh, I know.
Yeah. Today will be a shortened class, so we won't take a break. So if you're sitting, well, he's just not sitting there taking a break. At 10 o'clock, I have to get online via Zoom meeting. So for the college. So um, this is tutorial 3, designing a page layout, and I'm going to cover the highlights. There's a lot here that we're not going to go into because this isn't a full class on CSS. Now here's a page layout with floating elements. So you see the design here. If you're into web page design, then go through the tutorials in this particular. Uh, we'll go through the examples in this tutorial. Tutorials in a tutorial, and this will show you how you can have your items up here in separate columns, like a menu. Um, Here's your left and right sections are floated into separate columns. So you have this and you have this. And this is done better than like using a table. I can accomplish the same thing with using a table, but this gives you more flexibility in the formatting. And that's where the true power comes from. For example, in a table, I could start my table with a table, do that for my row, that's for my data cell, and then I guess I have writing first. This is the writing. So you can put it in a separate TD like that. Have the image in their own separate TD. And so you can have the writing right beside the image. So HTML gives that to you directly. What CSS gives you, it gives you the capability to format it, have more power in that regard, the menus in certain places, and so forth. And down here, the contents of the page footer are floated into separate columns. And I know that's kind of hard to see there, but I can't even see it. But just separate columns, basically. Again, I could come down here and I could put a table down here, but it wouldn't be my footer. I could put a table down here that has 4 columns and put each one of those in that column. But this just gives more power. See, this is the display style. Could be defined for any page element using display : type, where type defines the display type. Like here, you can display it as block, as a web page, inline within a block, treat it as block placed inline with another block. Some of these I'd have to really look at, create an example, see what in the world it actually looks like. Run in, displayed as a block, unless this next sibling is also a block, in which case it's displayed inline. So you can just see there's like a ton of different things you can do with that display style. Here's an example. Creating a reset style sheet. Reset style sheet supersedes a browser's default styles, provides a consistent starting point for page design. The first style rule in a sheet is the display properties display HTML5 structural elements. So you got display block. Just generally, the nav is how you do navigation. So if you want a navigation list, that's how you can create it. See, with the table, although you can do 100%, a lot of times it's based upon a pixel size, where you can put a width in there. But you can do the percent, and that's what you're talking about here when you're deciding on your layout, not just tables, but they're talking about all those elements that they got defined. You can say it's fixed, or you can say it's based upon a percent. So like on a table here, let's see if I can get this right. What that? Maybe that's emails coming in. Now I don't know if I can quotes around this or not. I'm gonna try it without it first. So put width is equal to 800. Come over here, and it's now hard coded. Problem with that is when you got a something that has a screen that can handle much more than that, then it's shrunk way to the left. When you got a small screen, it may not be enough to display it, and then it defaults to a number that may not be pleasing when you view it on that device. Now instead of 800, we could put we want to take up 50%, like that. Then I'll take 50% of my screen. Doesn't matter what. If I look at it on my phone, it'll take up 50% of my screen size of my phone. So it's no longer hard coded. And this is just telling you that you have the same opportunity to do that with these elements, the page design. Then you talk about the issues there. Now in CSS, over here on HTML, you do width equals, and then the number, or you can put that inside quotes like that. Remember, we had the width down here, so it affects more than just the table. You can do different items there. You can even, if I say the table's going to be 50%, actually, let me say this is going to be 800. See if I can put this in the right place. I'll put the width is equal to 600 there, and width is equal to 200 there. That's interesting. Oh, is it down there? Sure enough. But that is still weird. Because when I have the 800, everything appears under just fine. If I say this should be 600 and that should be 200, should add up to 800, right? Yeah. Unless I have this zoomed or something. Maybe I do. I do. There's 100%. That's a normal. I have zoomed so I can see. Okay, that makes more sense. So I'll make it bigger so we can see it though. Yeah, I figured I better go home if I have 600 plus 200 is greater than 800. But again, here it's different. You don't do the equals, you do the colon. And there's more more tags you can set this in, or more CSS that you can put it into. You see here, you can control the body. So you can have a maximum width for the body, minimum width for the body. This adjusts based upon your browser, and width is equal to 95%. So you see here, over here on the right hand side, you got this background showing through, because this is taking up 95% of the page. I don't think I know of any way to do this with regular HTML. I don't think this allows me to. I never have tried. I don't think 95%. See if I can get this right. ET color is equal red. I don't see a 5% of the screen. Well, let me get off my Zoom. I don't see a 5% over here showing the browser background. So it doesn't allow you to do that. Is that hurtful to eyes? Tan. There you go. A little bit more pleasing. Mm-hmm. Yes. I don't know if I remember how to do it, but let's see.
I'm just saying,
255, 28, 232. Hex code that. I'm guessing I have to put some kind of character in front of it. Is it a hashtag? Yeah. Now to find out this hex code, you have to go in some kind. But every package has it. It doesn't matter if you have Paint.net, Photoshop, or whatever. If you go to the color palette and you expand it, there's a place where you'll see the RGB, and most of them have the hex right there too. So. Uh-huh. This is when you're using a web design package like Dreamweaver, and you're choosing like a color for the background. It'll come up with the same little color palette, and you choose a color, and it automatically puts that in there for you. Now, I realize this is the old way of doing it. CSS gives you more power in that. This just changes everything in the entire body. But if I wanted to just affect like 95% of the page, and that 5% to be that other background, then we'd have to use CSS. Not in regular HTML, but in CSS, you can have different sections. Here's the margin left, margin right, and these are block elements. If you're, I'm not going to go into it here because I want to cover another topic. But again, if you're really into it, then if you look at the, if you do tutorials, they'll show you how to set this up, where you can break this into, like you say, pieces, and so you have more control. Where you can do a different color here and different color here. So. Let's see, where was I? Okay, so we got this div element. The div just defines a division. So, like a particular area of code that you want to point to somewhere else with JavaScript, that is. I'm thinking ahead on that. And here we got our H1 defined. By putting div on here, then this is going to apply these items to it. Height, display, vertical line, color. You can put color in there. You'd have to look up what CSS is, if it's BG color or background dash color. You know, those are the things that if I was going to do this for a living for web design, I'd probably want like buy a small book with all of them enlisted in there, so I could scroll through easily and find them. You can do floating point page content. There's no way you can float content with regular HTML. And you see it's a float : position, and then you put in none, left, right. Not sure why you put none in. Now here's what that does. Here's just an original layout. And when you put this right here, it just has this blank over here. But when you float it, then you have your content over here, and all this wraps around it. Float left. I'd have to read that to see what in the world it does. But down here are this is how you achieve having them center here, text align center. So each one of these is centered. So our horizontal navigation that we're defined here is this going across here. Float left. Maybe. It doesn't look like it's floating left to me, does it? What is it? It looks centered, doesn't it? So I'm not. Yeah, I'd say I'd have to read this closer to see why that's. But yeah, maybe it's the images that it's referring to there. Yeah. Hmm. So that would be on the right. I don't know. That's. I can go over all this. Float right looks like it should be. Oh wait. Oh, whatever you have here. If you're doing float right, then the other elements are left of it. So maybe, yeah, maybe they're right. Maybe it is the image there. Hmm. And I'll give you lots of examples here in the book if you're curious on that. See here, this is where you do 25%. So each one of these takes up 25% of that space. Now, not 25% of the screen, but just 25% of this right column. And see here, this defines the right column as 67%, left column is 33%. So that's how it's breaking them up into pieces like this. Let's see, what else is it doing? They're display blocks. So just displaying information. So it's the width of each list item to 25% of the width of the navigation list. So that's what the part achieves this. Now, for the most part, people don't do this manually. You have tools where you can choose like themes that do this for you. Have you ever created a website online that use one of those, Squarespace, something like that? Yeah, they make it so easy. You don't have to know any of the CSS. It's all based upon CSS. Um, I've used Squarespace. I think Squarespace is one of them. Maybe that was the payment part. I don't remember. What? Wix is one of them. Yeah. Um, there's that blogging type WordPress. I never have used WordPress, but I think it uses the same thing where you choose themes and so forth. So now, if you're going to work for one of those places, then you probably have to design the theme using all this. Um,
The project's gonna be like,
we had one CSS from last week, but the projects are going to be HTML, a little bit of CSS, not very much.
well, I mean, like the one that's coming up, like, being due really soon.
Well, I'm not going to sign HTML today, but next time I plan to get into JavaScript because I want us to get started programming early. So I'm still going to just briefly go over a little bit of CSS. Last time, what I did is I went strictly with the book, and we spent most of the semester just doing CSS. And I feel like that really didn't accomplish that. That's what I wanted. Right, because this should be an introduction to see if you like programming. Um, computer science is programming. Um, there's networking. That's the other piece. But if you can't stand programming, then you shouldn't take another programming class. So that's why I wanted to get into the programming early on. So, and since we really didn't get into JavaScript that much, we got a tail end of the last time I taught this. Not the depth I wanted to get into it. Not sure yet. I have to decide before next week if I want to assign my own projects or the MindTap. What MindTap does, some of you have done the web page, right? We went out and created it and so forth. It automatically grades it, so it tells you whether you're right or wrong. Did you have good luck with it being correct? Good luck? That's even better. That's a better tool, I think, than MindTap in that regard. Yeah, MindTap, I've had people turn in their CSS and it looked perfect to me. And I could even view it in an external page and look fine, but then MindTap would say it was wrong. So I'm not sure if I want that headache with JavaScript. But it does give you a tool to learn. So we're going to offer that in the spring. Or that's what I'm going to suggest that we have. Some popular CSS frameworks include Bootstrap. This is a term you see fairly often. Now, these last three I haven't really heard very much. YAML4, 960 grid system, Foundation 3. And a framework is a software package that provides a library of tools to design a website. Includes style sheets for grid layouts and built-in scripts to provide support for a variety of browsers and devices. This is talking about how to set up a grid. You can do the same thing with tables, but again, this gives you a lot more power. You can have a table go all the way over. See if I can remember how to do that. Okay, so I got TD there. My next row, TD column span, I think is what it is, 2. Let's see if that's correct. Except for I don't put borders on, I won't be able to know. See how that goes all the way over? Where this has 2 columns? So you got total control on like how many, I can put 5 columns in here, type of deal. No, if I want to do 5 columns, I'd have to have 5 TDs yeah. The column span goes over, takes up 2 columns. Now, if I said, if I had 5 columns in one of them, and I said 2 columns, then it would be like blank over here. And that's what I messed up on what package where they did the HTML design for me. I somehow deleted those cells over there, and I wasn't sure how to get them back in, so I had to go through HTML and fix it. But again, here you design your layout. And setting up your grid, a little bit different. You see you got your class equals row. It's the first column. So I got 2 rows, 2 columns. And that's nested within the first one. Okay, I'm seeing it now. That's just right here, where you got 2 rows and 2 columns nested in your first column. Now this right here is setting up the design of it. We got our div and so forth. Doesn't look like they put any code in there yet. Does that make sense on what that 2x2 does there? Could I program this from scratch? No. But I can, I can take this, I could edit, copy it, and I could then tweak it. I could get a 3rd column in there. Looking for patterns is important with work with HTML, CSS. Because to create a third column, I would need to copy this, right? That'd be one thing. And then the question becomes if this name means anything up here. Class equals column -2 -3. I don't think it does, but that's what I'd have to explore. I am not a CSS master. I'm fairly decent at HTML, CSS. I fumble around with because I don't do web design, nor do I want to.
Spaces that, like, for the parts underneath, are those necessary or,
Like the blank lines.
like, doesn't do it all on its own?
Oh, spacing doesn't matter.
Well, I mean, like the indents, I guess, you know.
Oh no, that spacing doesn't matter.
Okay.
Blank lines don't matter. You could put it all on one big line. It'd still work.
Oh, yeah. Yeah.
Right. Yeah, if this was all left aligned, I would have flipped over this slide so fast you'd wonder what was because I wouldn't even be able to interpret it. And that's generally in programming. I had one student one semester in a C plus class, and she was left aligning everything, no indentation at all. And she was having a lot of trouble. And I said, you really need to indent these based upon the while, the for, the if, and so forth. I said you'll find your programming to be much easier. Well, she for whatever reason didn't want to do it. She wouldn't do it. So I really couldn't help her very much with her code. She'd bring it up and just look like Ghibli gawk to me, you know, is it? Yeah, gibberish. Yeah. And she didn't finish course successfully. Indentation, you're right, is key to understanding what in the world you're looking at and recreating it. If this wasn't indented, I might have a hard time figuring out what to copy. I wish it was just text so I could actually copy it and show it. But yeah, you'll find some people claim it should be 3 spaces, some should be 4, some say you just do a tab. Yeah. Let's see. Okay, so this is where those word names are coming from. 1/3 and 2/3. 1-3 is 1/3 of the 1/3 and 2/3 width columns. So 1/3, 33% of this of it, 2/3, 66% more or less. So when they're referring to that up above, that's where those names came in. What's okay? Here they're just taking this and putting the code in now. So they're showing a build up of that chocolate page. You can do fantastic things with CSS. Typically, as a computer programmer, you do not go to this depth. That's if you want to be a webmaster. And I can go over all that. Might be the last I wanted to show. Okay, that's not that. Okay, here's where I wanted to spend most of my time. So I think this is what you'll have the most difficulty with. Make a gasp. You'll love it after this. I think I've left enough time to cover it adequately. So if you're wondering why I was going over so fast, people have trouble with Boolean, binary, and so forth. You hate it? We're not going to cover all the different topics in here. This is how the learning objectives here kind of really talks about how does an electronic device work. So you got a computer, you know, how does it communicate and so forth. We got the binary number system.
How much is that?
What? How much is what?
Program.
Oh, it's free.
That's what we think.
Yeah, it's Windows 10. Actually, there's a free version of it. Yeah, let me show you what Paint.net is. I think it's the best graphics package ever. Except it doesn't work right with my tablet here. I am getting approval for a new tablet, which I'm drawing tablet. Yeah. But my old one does not work well with Paint.net. It goes really slow, like it loses part of the keystrokes or the
Is
drawing.
there like a way to change the stability on it or something?
Not that I found. It's pretty old technology. These tablets.
Like,
I think Paint.net is one of the hardest packages to load or locate to download. If I go to Google and I type in Paint.net and press enter, you'll go to this website, getpaint.net. It probably is just important to note the URL after we get down to that point. But if I go to getpaint.net, comes up here, has all these, it has all these buttons all over the place. Right here is the key link, get it now, free download. So if I click that, then here you have to click the second one, the .pdn, and you actually click this here. If you click over here, it doesn't take you to the right place. But I click here. And then last but not least is this right up here. Actually, I guess you can't go directly to it. You have to actually, because this looks like a very generic. But now if I click this, it'll download a zip file. I extract the zip file. It's in 1.exe, double click it. It's very easy to use. Has many of the features of Photoshop. They're ripped off Photoshop. GIMP Shop is also a free one. That's it's ripped off Photoshop.
Well, I mean, considering how expensive Photoshop is.
Yeah. But no, this is the free one. I'm hoping the new tablet that I get will work with Paint.net. A binary. Binary is base 2. And you can use the digits 0 and 1. This is how your computer talks. So when I'm sending any information, like what I'm doing right now, as it's going across the circuitry, it's going across the zeros and ones. Now you don't actually physically see zeros and ones. The 1 indicates the voltage. So when a voltage is so high going across the circuitry, it's considered a 1. When the voltage is so low, it's considered a 0. A lot of people don't understand that it's not like this is 100% of the voltage going through. This is 0% of the voltage going through because voltage varies. If it's so high, then it's labeled as a 1. If it's so low, it's labeled as a 0. Now they have error correction codes that put into that. So when you send information, like you type in 3 in Excel and you press enter and it saves it in that cell, when that 3 is going across the circuitry, how does it not get confused and think it's 4 or 2? Or, probably that's a bad example because I don't know what the codes would be there. But it has the error correction on it. So it will automatically see, okay, that's not right, send it again. And so it'll send it again. So you'll hear all the time that computers talk by zeros and ones, but there's no zeros and ones going across lines. It's voltage. So we have a binary number that maybe looks like this. And we have this first blank, second blank here, third blank, fourth blank, fifth blank. This position here represents 2 to the 0, 2 to the first, 2 squared, 2 to the third, and 2 to the fourth. Powers of 2, because it's base 2. If we were dealing with base 8, if we had the same thing in base 8, this would be 8 to the 0, this would be 8 to the first, 8 squared, 8 to the third, 8 to the fourth. If we're talking hex, it'd be 16 to the 0, 16 to the first, so forth. So that's kind of the setup on it. Now, 2 to the 0 is 1. 2 to the first is 2. This is 4. This is 8. This is 16. So figure out what this number is. You take this number here, the 1, times the number here. So I got 1 times 16. You take this number here, this 1, times this number here. So I got 1 times 8. You take this number here, the 0, multiply times this number here. Yeah. Take this number here, multiply times this number. And take this number, multiply times that number. And 16, 24, 26, 27. Assuming I'm adding those correctly. This is binary, base 2 for 27. So if I'm have a variable in my program where I'm setting it equal to 21, this is the voltage pattern that's going across the lines to the RAM or whatever it needs to go to. Now it's a lot easier than multiplying these together, because do the ones actually do anything? No. So all you do is if you have this pattern here, when you're dealing with binary, wherever you have a 1, you just add those numbers together in the bottom. 16 plus 8 plus 2 plus 1. So it's pretty easy to go from binary to decimal like that. Now, if you have any questions or going along with this, holler. I haven't got the part of binary you think yet? No. I mean decimals. I don't think I remember. I think it's the still powers of 2, if I remember right. And then 2 to the -1, to the -2, I think. Yeah. It's been a year since I teach this all the time in Introduction to Digital Design and in this class, but I haven't taught either of those classes since last fall. And we haven't hit decimals really, of course. Okay, so that gives you kind of a little bit of background about that. Binary is the idea of on, off, yes, no, true, false, positive, negative. All data stored inside a computer is stored in binary, also called machine language, and interpreted display on the screen in human language. You couldn't program if you had to do all ones and zeros and so forth, I wouldn't think. You'd have to be like that person off the movie The Matrix, sitting there watching all the ones and zeros go across the screen. He knows exactly what's happening in the Matrix. I don't think most of us are that sharp that we could do that. So this shows that you got your external representation here. You got your memory where it's storing that off. Although, interestingly enough, whenever you examine memory, memory is displayed in hex. You don't see it in ones and zeros. Not sure why. Haven't really found a connection to that. But if you love binary and you want to go on assembly language programming, you'll see that what we deal with is hex. Base 10. This is what I was talking about. 2 to the 0, 2 to the first, 2 squared, 2 to the third. And then you just keep increasing your powers of 2 to however many digits you have. Typically, you have eight of those represent the byte. And then, though I was reading yesterday that there's, what class was that? They were talking about a ninth bit. The ninth bit used for the parity checking, to where there's even parity or odd parity. Like you have an even number of ones or odd number of ones. I don't know what made me think I was in the 8th position, but that mentioned the 9th position. What that means is I'm getting ready to send a number across the lines to you, in terms of like your computer circuitry. And this is what I sent across. And I got odd parity. What that means is I should have an odd number of ones. So this is actually with my data, whatever that represents. And bless you. Let's say this is what came across. This is what I received. What's wrong with it? Yeah, there's an even number of ones. This would tell me that it did not come through correctly. And so the programming, there's very low level programming there, then sends back, says, hey, send it again. Something's wrong. And then it sends it a second time. And, well, probably not there. But let's say this should have actually been a 0. So it sends it back the second time. And now there's 3 ones, isn't there? So the odd parity is checked. So that's a very simple check they do. Now the question becomes, if it's supposed to be 1 0 0 1 1, what happens if these are correct, but then 2 of these get screwed up? Your normal checking can't detect that. Now there is for servers, I think it's called ECC, error correction codes, where it can do that, and it self-corrects. It doesn't even have to send it. Somehow it self-corrects, and I haven't read much about that yet. But yeah, there's a lot there to make sure you get all of your results. But have you had flaky things happen on computers before? Like it just a real quirky thing never happened again.
I know what you mean.
Yeah. Right. You may never see it again. That's the nature. When you deal with voltage going across and you have limited error checking, then you have bizarre things happen once in a blue moon. And so people shouldn't get so upset about it and wonder, why does this occur? And it's like, calm down. If it happens consistently, we'll look into it. If it's just once in a blue moon, then we write it off that way. Here's the numbers from 0 to 31. And again, you could put 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth under each one of these. And then if you add those numbers up, they would give you each one of these. Now, converting from binary to decimal. Bless you. Binary to decimal. No, I think I want decimal to binary. I already showed you binary to decimal. This is a way you can go from decimal to binary. There is a shortcut to this. I show this technique because this is a technique works no matter what your base is. If you're working with octal, if you're working with hex, this will work. Let's say that I have, clear this off. Um, 231. And I want to convert this. This is in our decimal. I want to convert that to binary. Well, step one says to write down the following chart. You actually only have to go up high, as high as the first number below this. So I got 231 or equal to it, I guess I should say. The first number below it is 128, right? So that's really all I have to go up to. Let's see, 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth, fifth, sixth, 7. 2 to the 0 is 1, 2, 4, 8, 16, 32, 64, 128. This used to be meaningful. These were how memory was originally. 16K, 32K, 64K. Yeah, 128K. I think that was like that was a big one when I was in the 80s. Wow. Now there's like gigabyte RAM. Yeah, and we're not talking about disk storage space. We're talking about RAM. So yeah, imagine working with 64. Commodore 64, you ever hear of that?
Yeah.
Yeah, 64K of RAM, which means you could not declare 100 variables because it wasn't room for it. You had to be really clever in your programming. Now you can be sloppy in your programming. You see, if you take a programming class with me, you'll see me be sloppy because the memory's all, we got so much of it, it's like I've never exceeded it with my variables. So, anyway, I digress. Okay, find initial key number. The key number will be the number being converted. So initially, my key number here will be 231. Then, old style divide the key number by the number in the bottom row. Step one is less than or equal to the key number. So I look for the first number that's less than or equal to it, which is 128. Goes in 231 one time. Geez. 103? It's bad. I still teach math, but okay. Yeah. It's a good thing the weekend's about here. Place the answer in the blank above the number you divided by, and the remainder becomes a new key number. So this one here, I put in the number I just divided by. And this becomes my next key number. Now we look for the next number that's less than or equal to that, which would be what? 64? And 64, 4 goes now one time, so I put a 1 up there, of course. 1 times 64 is 64. That gives us 39, I believe. Yeah. And this is my new key number. Now I'm looking for the next number that's less than or equal to that, which would be what? 32. And that goes in there one time. Subtract that, and this is my new key number. And we put a 1 above the 32. I look for the next number that's less than or equal to that, which would be what? It's been a rough week for a lot of people. Though I'm not sure I'm not making a math mistake, but at least you'll see the idea. So then I put a 1 here. Now I'm looking, this is my new key number. I'm looking for the next number that's less than or equal to 3, which would be 2. That goes in there 1 time. Subtract that. So put 1 here, and this is my new key number. I'm looking for the next number that's less than or equal to that, which is 1. In case you're wondering, there is a shortcut. If you see a shortcut, fantastic. Put a 1 there. Now, if the key number is not 0, go back to step 3. That's what I was doing. I was repeating that over and over. Put the zeros in any empty blanks. No leading zeros, though. So I put a 0 there and a 0 there. And that is the binary representation of 231. The shortcut to it is you just this method here really helps you when you're like trying to convert 231 to base 16 or base 8. So that's why I show this. The shortcut to it is you take 231, you look for the first number that's less than that, less than or equal to that. You put a 1 there, and then you subtract it, and then you keep going down. So you don't have to actually do the division. You can do all subtraction. I like to show that because, again, it demonstrates all the bases. They give a different way of doing it here, but I don't like their way. I've taught this in a tech math class for about 3 or 4 years now. And I finally just came up with that step by step to help people with this, even though it's not a shortcut. It doesn't matter. Now, if I did have parity on this, like I was then if I decided I wanted even parity, for example, I'd have my extra bit out here. And even parity, what would I put here? I put 0.
Oh, really?
Because even parity means I have to have an even number of ones. Well, this is if you're not in terms of converting, but this is from the electrical design standpoint. Like if I was writing it to do the error correcting, then you'd need a 0.
What happens if you need the odd parity?
What do you think I'd put there if I needed odd parity? A 1.
Okay.
Because there's 6 1s. If I put another 1 here, I'll have 7 1s. And so that helps ensure that one of these bits going across isn't messed up. But again, if you have 2 or 3 of the bits messed up, then you think that's weird, you shut down Excel and you load it back up and it works. Now this is the part that I really have. I understand examples in the Introduction to Digital Design class, but you can overflow the size. Because if you got like 8 spots, bits, then if you do an addition or subtraction, then you can have it exceed over into the next bit, the 9th one, and you have to handle that appropriately. So. Here's a make sure I didn't skip any slides. This stuff's harder than the CSS. Signed integers include negative numbers. Signed magnitude notation uses 1 bit for the sign and the rest for the value. Now 5 is this 101. So it's just those right there. When you put a 0 in front of it, that indicates a plus. When you put a 1 in front of it, it indicates a negative. Two's complement representation To make the negative of a number, flip every bit and add 1. So like 5 is this right here. And so for the to make the negative of it, you flip every bit and then add 1. Let me show that. Well, that shows it right here. When I say flip a bit, 0 becomes 1, 1 becomes 0. That's what we did off of this original 0, 1, 0, 1. And then you add 1 to it, and that's where you get this right here. Now, if you have 0, initially, 0 is all zeros. If I flip every bit, all those zeros become 1s.
Okay.
And then I add 1 to it, and all of a sudden it goes to zeros. Let's see. I think this will demonstrate it. If I look at adding on binary, the only digits you can use are 0 and 1. So 1 plus 1 would normally give us 2, wouldn't it? I can't have a 2. So what do you think I put here? 0, and then I carry a 1. 1 plus 1 is 2, so I put a 0, carry a 1. This is a really weird one. 1 plus 1 plus 1, you probably wouldn't get unless you've seen it before. It's 1, and carry the 1. Because when you think about it, 2 of these gave us a 0 here and carried a 1, didn't it? So when you have another 1, it's 1. I know it's bizarre. But 1 plus 1 plus 1 gives you 1, carry a 1. And 1 plus 1 here is 0, and you carry the 1. This is what I'm talking about. If you don't have actually you have space for this, you have to handle it. If you're designing, electrical engineering designing, then you have to handle that appropriately. Right, voltage. There's I don't think I remember. I can make up an answer. Not even sure if we get to that in Introduction to Digital Design, but they got these arithmetic logic units inside like a circuit, and so your voltage comes in there, and then inside there it does this. How it actually does it from a physical standpoint, I'm not sure if I've actually ever read that. If I have, I don't remember it. Does that make sense? How this is being done inside of like a. So 1 plus 1 here is 0, carry a 1. 1 plus 1 there is 0, carry the 1. 1 plus 1 there is 0, carry the 1. 1 plus 1 there is 0, and we'd normally carry the 1. But remember how this over here, we only got the 4 bits to work with. So then that extra bit that you carry, sometimes you just drop it. That seems real weird, but that's like some of the algorithms you'd see in that class. You just drop the 1. And sometimes it's used to indicate what the sign should be. In this case, it could be the 1s is used to indicate it's becomes a positive, back to a positive 0. So, floating points use binary scientific notation. I don't think I've ever done that. I'm sure I did last fall, as I went over this. Looks like the same. You just move it, but powers, you move your decimal point, it becomes powers of 2 instead. So for example, I'm pretty sure I've never seen this in digital design. Like this right here. How many places would I have to move it? 2. Let's move it over to there. But instead of being 10 to power, it'd be 2 to power. And since we moved it to 2 places, it'd be that. Yeah, because binary means you don't use a 2, right? And here all of a sudden they're putting a 2 here. But in decimal, base 10, do we have a digit that's a 10? No, our digits are 0 through 9, aren't they? But yet they put a 10 over here. So I guess you could use that same logic of why they could use a 2 here. Now, ASCII, Unicode, they're mapped into binary numbers in a standard way. I don't know if I could actually find a table for that. And actually, it's a website, I think. I don't know why they got it, but ASCII table. Many ASCII websites. Which one do I go to? I'm gonna get a bad virus one of these days. Oh, ASCII table. That's one I always go to. Very first one. I don't know why I didn't see that. So yeah, when you got an A, they never include binary in these tables for some reason. But if you got an uppercase A, see how it's mapped to hex 41? That's 65 decimal. So I could convert 65 decimal to binary, and that would give me my equivalent. So when we're talking about, and again, you have to realize what you're sending across the lines and so forth. But when you're talking about different letters, you can encode them the same way. Because when I type A in, like into Excel, it's going across the circuitry, isn't it? So it has to be transformed to ones and zeros. I'm running out of time, so let me. Some of this you can read in the book and see they talk about amplitude and waves and so forth.
Is there a way to access
I can put them out there if you want them. Okay. Oh yeah. Are you having trouble too? Is anybody else? So they fixed half of you, but half of you still can't get in. Now you sent. I got his down, but you send me an email to remind me, and I'll forward it on to our bookstore lady. So, yeah.
Okay.
Right. You were assigned into a different account? I didn't realize you could do that. So when you created I don't know. Oh. So when you create your Cengage account, I see what you're saying. They never have told me what. I always just send it on the bookstore lady and she fixes it. Um,
Lord.
that's interesting. Okay, yeah, but send me an email and I'll forward it on to our bookstore lady. Guess I should have asked that. Well, what was wrong with that? So just send it on. And they tell me it's fixed. Um, when you got signals going across, um, this talks about the wave pattern of them. They're not going across as straight lines. They're waves. So that's what this is referring to here. RGB encoding scheme. Colors are combinations of red, green, and blue. 1 byte each for red, green, and blue. Raster graphics store picture is 2-dimensional grid of pixel values. They're helping you see the digital representation of these items. Then you got your individual pixels. So 1 byte each for red, green, and blue. And Raster graphics store pictures as 2-dimensional grid of pixel values. So when you got a picture, you have a lot of voltage, a lot of ones and zeros going across the lines, don't you? Representing the different pixels. Now, I took a class in this. It's kind of an interesting class. I don't mean to digress again, but it was a wavelets class. And the idea is that video is transformed in some manner. Because if you send your video over and you take each individual piece, with appropriate voltage and electricity going across and the waves and so forth, you would never be able to watch a movie. So like your phone, you're watching a movie on it. Well, the reason why you can do that is because it transforms it into a smaller signal. If it sent each one individually, then that would be horrendous. So there's patterns to it. How would you send less patterns on this, do you think? Um, could be. Maybe changing the amount of colors. Can I reduce these colors such that for the visible eye, you can't tell the difference? Um, sometimes and this one's kind of hard to see, but there could be like there's huge amounts of this ton are the same color. So instead of sending them through individually, you can send the color through once and then say it's from this follows this like polygon pattern. There's lots of different ways to do it, but now what I really want to get out of the class, I want to be able to program my own program to write like a MP4 or audio, MP3. That's what I really wanted to get out of the class. It was all theory based, but I wanted to know how to do it from the programming standpoint. That's what they're constantly doing. How can I transform a movie into a smaller signal so you can receive it faster on your phone? So, like if I want to download Gladiator onto my phone, I click the button. 1 second later, it's completely downloaded. It's no longer like streaming or anything. It's on your phone. That's what the big quest is for that. You say good, yeah. Well, it's more than just zip. It's transforming They use a lot of algebra. Actually, you'd be surprised. A lot of logs in it. Yeah. But yeah, you'd be surprised where the technology's come. If you look at 15 years ago, where phones were, and what videos you can send to it now and have them look good. That's a big key there. It's a world of difference. Yeah. Now it's just, yeah. And then who knows where it's going to be 5 years from now.
Home things.
Yeah.
They're already around.
Yeah. Probably. Or a chip they put in your head, and you can watch movies in your brain. And okay, this is talking about what is the space necessary to store the following data: 1,000 integer values, 10-page text paper, 60-second sound file, 480 by 640 image. We go through all those, an integer value, and figure out, how many bytes you need, bits to represent it. But we're not going to go to that. Data compression is storing data in a reduced size form to save space and time. Lossless, data can be perfectly restored. Do you need the video perfectly restored on your phone? It's so small, you're probably not going to see it that good anyway, are you? Yeah. Lossy is where data cannot be perfectly restored. So I guess that most video transfer is lossy format. What does YouTube do as it detects you have a poor internet connection? Yeah, and most of the time you probably don't even notice it. You're sitting there, it's just like you're watching a video just like normal. Occasionally it drops it down to the point where you do notice it. Yeah, you're sitting there, what's wrong with this? And yeah, we had that when first of this semester when we were having the internet troubles here. Some of the videos I uploaded, I'm looking at them, it's like, this is horrible. You can't see it. And then I go and look at the quality, and it's dropped it down to the lowest. I didn't know 420 was lowest, but yeah, it dropped down the lowest one. Does it? I don't know, but I was surprised when it dropped it down. That's the idea. Most of the time, when it drops it down quality wise, you don't notice a difference. Some of you play games. You look off with a mountain in the background, and they'll put an image out there. Because if you put it out far enough, it doesn't matter that it's not really 3D. If you put an image out there, it looks like the mountain. And how good does it have to be? Well, since it's placed far enough in the game away from you can't see it, quality doesn't matter as much. So there's a lot to take into account there. You have to think about where you're delivering it to and so forth. Anybody ever work with video that isn't compressed in any form? No, I probably told the story already, but I created a couple of video courses for World Quant University, and they flew me out to Columbus to create one of the classes, and I was in a recording studio, and very high quality, and I mean it took up a ton of space, the uncompressed format, and it was just like what you'd see in a movie theater. It's just fantastic what they'd come up with. I tried the same thing at home, and I think I came up to like 1 terabyte on that file in no time at all. If you told me it was 1 minute, it wouldn't surprise me. And I'm thinking, well, there's no way I'll be able to create a 10-minute video. I don't got that much, storage space. Yeah, so if you do any video editing at all, it's automatically compressed. There's no way your hard drive would be able to store it off otherwise. This talks about fixed length versus variable length encoding. And so they show you examples of that. And this talks about magnetic cores represent the binary values. If you're into science, that probably means something to you. I haven't had science in a long time. It talks about how transistors work. Those are really reading things. There's really nothing to show on that. Hardware side, yeah. Working 13 years as a programmer, I never had to do binary ever. Yeah, this. I don't even think I ever had to do hex. Now it depends on what kind of programming you're doing. I did higher level programming. If I and this is really even at the computer engineering side, but if I'm writing a program for this remote, I'm probably going to have to be at low level. I probably have to work with binary, maybe hex and so forth to debug it to figure out what's going on with it. Not that I don't even know how this works. I'm assuming it has circuitry in it. I never have took apart my watch, but if I'm trying to program this, the electronics behind it. Again, it's such a low level, you probably will have to work with the binary and hex and so forth. If you're writing a shipping system for Cali, such that they can keep track of everything they ship out, track it and so forth, you're not going to ever use it. Now, if you're going to Wichita State, if you're going to transfer Wichita State and major in computer science or computer engineering or electrical engineering, then you'll be doing so much of this that you'll be sick of it.
Already sick of it.
Oh, really? You did? I was gonna say, I need to do all that.
Yeah. Now, this is Boolean logic and gates. And Boolean logic is ruled for manipulating true, false expressions for binary machine language. Boolean expressions can be converted to circuits. You may have in one chip, one extensive chip processor or something like that. You may have a million circuits. Of course, machines are designing those. There's no way a person could sit there and how long would you take to put a million circuits in there at that microscopic of a type of level. And that's what we see in the introduction to digital design is that by doing some kind of change to your Boolean and or gates and so forth, you can achieve quite a performance gain. When you multiply that times a million, all of a sudden, at 0.00001 seconds, you're saving times a million equates to, something you'd noticeably see on your computer. Now, this is something that you run across in programming where you're just talking about Boolean expressions. X is less than or equal to 35. Question is if that's true or false. Well, it depends on what X is equal to, right? But that returns, like I said, true or false, 1 or 0, and you use that all the time in programming. I don't know why they have this here. It's not exactly a Boolean expression. It is in Visual Basic. Most programming languages has 2 equals. But 2 equals means you're checking to see if A is equal to 12. 1 equal in almost every programming language is an assignment operator. It means you're assigning 12 to A. You can have ands in there, ors, nots. I don't think I ever did anything like that.
I have no idea what that means.
It'll make more sense once we get to JavaScript.
Oh, okay.
Because then you'll see actually this is kind of laying the foundations of it. You got truth tables. Truth tables like you got 1. You can have 1 1. You can have 1 0, 0 0, 0 1. I didn't do those right pattern, but what? Or binary. Yeah. Now you might have this like X or Y. You can have X and Y. Now the OR is represented as a plus, as the operator. This is represented as what looks like multiplication. And so this is coming through, and you got X or Y, and you treat it like a plus, more or less. The one weird part is this one right here, 1 plus 1 gives us 1. But everything else is 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1. So it's kind of like you treat it just like addition, except for 1 plus 1 is 1. Where's this used at? You have two lines coming in. For example, you have a something coming off this circuit, and you have something coming off this circuit, and they're coming into an OR gate in your circuitry, and then this handles it appropriately. And this is bizarre as it seems how they handle a lot of the processing that's done on the digital devices. Now, and you treat just like multiplication. 1 times 1 is 1. 1 times 0 is 0. 0 times 0 is 0. 0 times 1 is 0. This is where you build those tables. Truth table lay out all the possible true and false values for Boolean expressions for each possible true-false input. And they don't do that's bad. Don't put zeros and ones there. False and true. Remember, false is 0. 0 times 0 is 0. 0 times 1, 0. 1 times 0, 0. 1 times 1 is 1. It makes more sense when you have zeros and ones there, because you can think of it mathematically. Here's a plus. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. So those are just our truth tables. Now the not. This is very useful in programming. Sometimes you don't know how to flip something to the opposite. Sometimes it's easy. It's sunny. What's opposite of that? Could be either, right? Not sunny. So we put a not in front of it, and that makes it easy, right? I'm in the room. What's opposite of that? I'm not in the room. Yeah. I may not be outside. I may have burst into flames or something, and I'm nowhere. Now this is, that's pretty easy. You just flip that. You could actually probably think of the opposite of that. But when you come up with something that's kind of bizarre, like in programming, maybe you have something that looks like this. And it's working exactly opposite of what it should. Well, what's opposite of that? I have no clue. So we put a not in front of it. In programming, sometimes that's just an exclamation. I cannot think how many times I used that over the years where my program was working exactly opposite like it should. And I could have sat there for an hour trying to rewrite it, thinking, well, what should this be? When it's really just as easy as putting the not in front of it. All that does in terms of the binary is it flips it to the opposite. 0 becomes 1, 1 becomes 0. Really, it's just where you programmed it. You thought you were doing it just right. Like you thought this is the way the code should work, but then when you ran it, it did the exact opposite. So you knew all I had to do is flip that around. Right. Like they told you, like X is sales maybe. When sales is greater than 30 and costs are less than 2, then we wanted to do something. And you think you have it down pat. It's like, this is it. I understood what they said. And then it's working just the opposite. That's where you can rethink the entire thing if you want. Usually companies don't want you to do that. I don't know how many times I've heard, well, this program's horrible. Can I go back and rewrite it? I said, no, well, we got other projects for you to work on. We don't got time for you to go back and rewrite this just because you don't think it's written. correctly. There's only 2 times I can think of where they actually let them go back and rewrite them. Well, one time I should say. Um, One was a budget program that was written at IFR. The person that wrote it just did a horrendous job, and you couldn't understand what in the world the code was doing. And this guy I worked with, he's a really good programmer. He said, "You want me to make changes to this budget program, but I can't. It's just written just as poorly as can be." He says, "I can rewrite it faster than I can to make the changes you're wanting." And they said, "Okay, we'll go rewrite it." And he had it rewritten no time flat. This guy was a genius at programming. I wish my skill level was even close to what his was. The other time was at Coke. I ran across coding like this, where they named all their variables like A, B, C, D, E, F. There was no useful variable names. And when you saw this, you asked, "Give me a practical purpose," and this doesn't seem to have any. What's X? What's Y? And I was looking at the code, and they were using go-tos. It was called spaghetti code. And I went back to my manager. I said, "There's no way for me to figure out what in this world this is doing. This needs to be rewritten." And he took the project back from me. Now, he might have found somebody else that was willing to look at it and figure out what in the world was going on, or they rewrote it. Let's see. This talks about transistors, grounds. I can go into that. This is like a computer circuit. This is what I was talking about, where you have inputs coming in here, and you have your circuit here, and you have your outputs coming out here. This circuit design is what you study in Introduction to Digital Design, the OR gates, the AND gates. How does it process all that? How do you have 2 numbers coming in here? Somehow this adds it and then sends this out. So, and again, we study it just from the theory side. How it actually works physically, I don't think I've read. Convert a circuit to Boolean expression, start with the output, work backward, find the next gate back, convert to Boolean operator, repeat. Doesn't mean a whole lot unless you've done it. By the way, there is, to create these efficient designs, there's software that'll do that for you. So it'll go through and you kind of give you're starting what you're trying to achieve, and it optimizes it. Example from text, build truth table. I'm not very good at actually doing what they're implying. That's where you look at your output, and using your output, you can go backwards and figure out what your design should be. I'm not good enough to look at this to see if this is an and or gates that give you this. This is an example of a circuit diagram. If you're just excited as could be about circuits and you want to take that Introduction to Digital Design class next fall, but you have these are voltage coming in. These are inverters. They change this. Now, inverter might be a switch. Like when you don't got the switch on, no power is going through, right? You flip the switch, and then it causes power to go through. So it goes from 0 to 1. So you can view these as switches that you hit. And then depending upon if the voltage is going through, maybe this is coming in from a different line, and when you push this and that voltage goes through, this causes maybe a garage door to go up, type of deal. It's this one AND gate here would not do that, but you get the idea. That's more than what we're going to cover. This right here may not be the most efficient design for this. By the way, you notice the multiplication there? That tells me an AND gate. This plus here tells me this is an OR gate. So this, if I were to write it down, A is coming in here, and it's coming into this. B is coming into this. And so this is going to be an and. So that's like that right there. Then this is coming down here. It's going through an inverter. Now that represents when you invert something, you put this little mark here in the theory side. And this is not A, this is not B, and they're coming into an and. So this would be not A and not B.
That's playing it on computer?
Oh, this?
Yeah, is that like, yeah.
I think it's a single quote goes straight up and down. So
Oh,
I think. So I don't think so. And then it goes through both of these, then come in to this this plus here, this OR gate. See, the question becomes, can you simplify this down? And there'd be properties you go through. That's actually what we're covering now in the Introduction to Digital Design, to see if you can come up with a simpler circuit. There's one example we did where it's really convoluted up here, and then it ended up just having like A coming through, straight through. So it was like you replace all this circuitry with just a straight shot. Oh, did you? Yeah. Well, we're not going to that depth. So if that's part you hated, we're not going to do that in this class.
Not that bad. That's wrong. That's
Uh-huh. I have to admit that Introduction to Digital Design class is not my favorite class. If I could figure out somebody else I could pawn that off on, I'd be just as happy as could be. Assembly language too. But Wichita State requires them, so somebody has to teach them. Yeah, I don't think it's that fun to design those things. But I suppose if everybody's different. If you like the low level, you love this stuff. If you're at the higher level, you like programming in Java and Visual Basic and C#, then this is not that exciting. That's why you see me skipping over some of this stuff, because I don't find it that exciting. And it's not that complex where, you can't just read the book and see it. This is where we're getting into designing a circuit where you're maybe performing some mathematical operations. And so this talks about input is 2 unsigned in-bit numbers. Output is 1 unsigned in-bit number, the result of adding inputs together. So this is where the inside, the circuitry, you're asking, how does it work inside? I have no clue. The mechanical side. All we really see is it from the design side. Here, this is coming into our adder. And the adder is a circuitry. We got 0, 1, 1. So we got 3 inputs coming in. So if we add those 3 numbers together, what's that give us? 1 plus 1. Now, not thinking in terms of the going back. Remember we did the binary addition? 0 with a carryover of 1. So that's what this is talking about, where we got 0 here and carryover of 1 here. This down here, 1 plus 1 plus 1. 1 with the carryover of 1. So this goes right hand in hand with that example I showed you. And by the way, the output is what's coming out there, your sum digit and your new carry digit. So then you'd handle that in whatever manner, like you receive that back and display it on the screen or whatever your end goal is. Yeah, exactly. You have real low level coding that how do you handle it when it returns a 0 and a carry of 1? And so then you'd handle it, in whatever manner. Now, the whatever manner you handle it in goes hand in hand with what kind of adder it is. So, whatever circuit design they have for that. And there are some of those circuits are cheaper than others. So they'll tell you not to use this type, but then to use this type. So this would probably take me a long time to simplify this. But this shows you the sum output for the one add circuit, whether it could even be simplified or not. Here you have A coming in. Here's an inverter, so that flips it to not A. Then that's coming into this AND gate along with not B. So not A, not B is coming into here, and then this is coming out from C. Yeah. In an introduction to digital design class, we'll get into the point where we're designing things more complex like this. And when I'm creating it with the software, my eyes start crossing, and it just it takes me a while. Here's a more advanced diagram, the one add. So this shows all of it. You have your inputs coming down here, and then, yeah. Now, I didn't cover it because it wouldn't make any sense, but that's what it's like achieving down here. So not A, not B, C, ands between all of them. Plus, if I were to sit there, I could create this diagram you see down below. It'd take me a while. And here's a complete full adder. It's coming in. Running out of time. Let's see if there's anything. This talks about different design of circuits. I'm not going to have you design any though. There's labs in some of this, but I'm not assigning any of the labs on it. Just reading it in the test is all that we're going to have out of this. Everybody knows what a register is, right? It's very you have some memory where you have to go off and retrieve it like from your random access memory, perhaps from a hard drive or so forth, and so you got different kinds of memory like that. Your register is these spots you have available where it doesn't have to go and retrieve that from all those locations. You retrieve it directly, and it's very fast. So when you're trying to add numbers together, for example, how it works is it transfers those into the registers. They got I forget how many, 15, 16 registers. There's only like 9 or 10 you can use. It transfers those numbers in and does all that within there, transferring the register information over to here, to the multiplexer, doing whatever calculation, and so forth. So it's all done at the register level, so that's very fast. Sounds weird, but it's more efficient to transfer it from the random access memory, which could be a bunch of locations, right, into these 10 spots perhaps you can use to do the calculations. Here's the key things to get out of this. You shouldn't sit there and be expected to computer science to know how does a multiplexer, explain a multiplexer circuit. You're not going to ever be asked that. Let's go to Wichita State. Then perhaps you would. Has anybody gone to Wichita State? Nobody's planning on going to Wichita State? Oh. Computers use binary representations because they maximize reliability for electronic systems. Many kinds of data may be represented at least in an approximate digital form using binary values. We saw that. You could represent a number that way, couldn't you? You could represent A, B, anything going across. They even demonstrated you could do colors, RGB, would be short Ds. Data can be compressed. Data must be compressed in most cases. Lossy, some information is lost in the process. Lossless, no information is lost. Boolean logic describes how to build and manipulate expressions that are true or false. We talked about that. We can build logic gates that act like Boolean operators using transistors. Circuits may be built from logic gates. Circuits correspond to Boolean expressions. Sum of products is a circuit design algorithm, takes a specification, ends with a circuit. We can build circuits for basic algorithmic tasks like comparisons, arithmetic, and control. These are things you'd actually do in programming. You're doing a comparison. You're doing some kind of calculation. And then the control down here. I'm not sure what that means on that. I assume it means like the program flow, but maybe not. Like while loops, for loops, and so forth. Yeah, I'm not sure about the last one. These two, though, definitely that's your comparisons that do occur in the while and the for along with the if, and then you're adding. Well, I'm going to put the test out here for chapter 4. That'll be the only thing for this week. Next week, I'm going to touch even less upon CSS. I'll just briefly talk about maybe a couple topics out of each of those units, not assign anything on it, and then we'll start focusing on learning a program. I think it's due Monday, isn't it? Yeah. From last week. Yeah. Web page? No. Yeah. Yeah, it's not a real complex page I'm looking for. I suppose you could put it all in one, but it's like one's just like a web page, and then the others are CSS. Like where you put CSS in a tag directly, you put one in CSS in the header section, and put one CSS in an external file.
Well, I wasn't here last week, so
Oh.
Yeah, I wasn't here. I watched it.
Yeah. You shouldn't have much trouble. If you do, let me know. I can push that Monday due date out. But all right. I better save this video before light crashes.